Section 6.3 talks about the law of large numbers. The law of large numbers, also called the law of averages, applies to a process for which the probability of an event A is P of A, and the results of repeated trials do not depend on results of earlier trials. They're called independent for this reason. The law of large numbers states, if the process is repeated through many trials, the proportion of the trials in which event A occurs will be close to the probability P of A. The larger the number of trials, the closer the proportion should be to the probability of A. We talk about the law of large numbers because in short term or short number of experiments or trials, the proportion of outcomes can be varying from what we would expect the theoretical probability to be, but over a large number of trials, we expect the probability and the proportion that we see to show closer to the theoretical probability. So for instance, here's a chart which shows how many ones were rolled on a six-sided dice. And so it shows us the proportion or the percentage of ones, starting out with a really low proportion of ones, but then over time, if we keep count of how many ones have been rolled, it starts to get closer and closer to what we expect the theoretical probability to be, about 0.167. So for small number of rolls, the proportion of ones may differ significantly from the theoretical probability. But for large numbers of rolls, the proportion will be closer to the theoretical probability. That's what the law of large numbers is telling us. So here's an example here. It says a roulette wheel has 38 numbers. 18 are black and 18 are red numbers. And the numbers 0 and 00, which are in green. We're going to assume that all the outcomes, the 38 different numbers, have equal probability. So with this in mind, what is the probability of getting a red number on any spin? And it says then if patrons in a casino spin the wheel 100,000 times, how many times should we expect a red number? Well, first off, if we take the probability of a red showing up, there are 18 red numbers out of the 38 different places that it can stop, 38 different outcomes. So 18 divided by 38 gives us a 47.4% chance of it falling on a red. But again, that's the theoretical probability. We might do this a few times and not quite see exactly this percentage of red show up, at least at first. However, if we were to run this 100,000 times, we would expect that the percentage of red to be around 47.4% of those 100,000 spins, or 47,000 times is where we would expect after that many spins of the roulette wheel. And we can assume that we're going to be getting closer to this for a large number of trials or a large number of spins, because that's what happens in the law of large numbers. This is connected to another situation, and it says here, suppose that the insurance company sells a special type of insurance in which it promises to pay you $100,000 in the event that you must quit your job because of a serious illness. Based on data from past claims, the probability that a policyholder will be paid for a loss of job is 1 in 500. So with that in mind, should the insurance company expect to earn a profit if it sells the policies for $250 each? Because they have to cover the cost of any potential payouts and have a little bit left over for profit. So we have to see if that's going to be enough in order to do that. So for the insurance company at least, if none of the policies are claimed, then all that money will go as profit. However, if all the policies are claimed, then they'll have a huge loss due to having to pay out a lot more money than they're taking in. But due to the law of large numbers, they should expect to sell as many policies as they need to ensure that the probability of the payouts is going to be around a certain number. So the more policies they sell, the closer the number of payouts will be in the probabilities to that 1 over 500 number that they would expect. So let's consider the fact that the probability of a claim is 1 out of 500. If we think that they'll sell, let's say, 1,000,000 policies, and if 1 out of 500 probability of having to pay, then if we multiply that, it means that it'll be somewhere around 2,000 claims that they have to pay out. So for each of those claims, they have to pay out $100,000. So if that's the case, 2,000 times $100,000 means that they're having to pay out, in that case, $200 million. The thing is, they're going to have to pay that out, but they're collecting the money for 1,000,000 policies. So the amount that they're paying out actually comes out to an average of $200 per policy, which is actually going to net them a profit if they charge $250 a policy. So if they're charging $250 a policy and on average paying $200 out per policy, then they're going to get around $50 on average per policy in profit. We call this calculation here the expected value. It helps us understand the expectations on, in this case, profit, giving the probability of something happening that causes a payout of money. So the definition here is the expected value of a variable is the weighted average of all possible values. Because it is an average, the expected value will be likely to be close to the actual value only when there are a large number of events. So the law of large numbers would come into play. The more events that we can have here, the closer we'll be to the real expected value. So here's how we calculate the expected value. Expected value, what we do is we take the value of an event 1, multiply it times the probability of event 2, plus the value of event 2 times the probability of event 2. And so we just multiply value times probability plus value times probability. And if there's more than 2 events, we can continue to do that for all the different events beyond just 2. Value times probability, value times probability. So here's an example of trying to use the expected value to estimate profit or loss. It says you're at an art auction, trying to decide whether to bid $50,000 on a particular painting. You believe you have a 1 in 2 chance, 50% probability of reselling the painting to a client in New York for $70,000, and a 1 in 4th chance, or 25% probability of reselling the painting to a client in San Francisco for $80,000. Otherwise, if it doesn't sell either way, you'll have to keep the painting, which has benefits, but not necessarily here monetary ones. So what would the expected value be of a $50,000 bid? Knowing that you might be out that $50,000, or maybe be able to resell it for different prices, but with different probabilities of actually being able to sell it. So the way we do the expected value here is, first off, we start with negative $50,000. Because that's going to be how much the payout will be to actually purchase the painting. So that's a negative amount times 1, because if we buy the painting, then it's a certainty. So given that the purchase has been made, we'll be out $50,000, negative $50,000 plus, and then we take the probability of being able to sell it for $70,000 times the probability of 1/2, plus the other option of selling it for $80,000 and with the probability of 1/4. So we take 80,000 times 1/4. So we take cost times probability plus earnings times probability plus earnings times probability. And when we do all this, it's going to come out to be $5,000. And what that means is, on average, the expected value is a $5,000 profit for this particular painting. Given the three different outcomes that could happen: keeping it with a loss of $50,000, selling it for $70,000 with a probability of 1/2, or selling it for $80,000 with a probability of 1/4. We would expect to receive on average a $5,000 profit. Another example of expected value here is with lottery tickets. It's supposed that $1 lottery tickets have the following probabilities. There's a 1 in 5 chance to win a free ticket, which is worth $1, a 1 in 100 chance to win $5, 1 in 100,000 chance to win $1,000, 1 in 10 million chance to win $1 million. So given the probability, what is the expected value of a lottery ticket? And winners do not get back the $1 they spent on the ticket, so it will always be out that $1. So here's a breakdown of how we would do expected value. Again, it has to do with the value times the probability. The value of purchasing a ticket is -$1 since we spend that dollar. Probability is 1 since it's already been done. It's a certainty if it's been already purchased. Then, however, there's a 1 in 5 chance of winning $1, a 1 in 100 chance of 5, and so on. Value, probability, value, probability. And we go through and we multiply each value by its respective probability. So -$1 times 1, $, $1 times probability of 1/5, 20 cents. $5 times 1 over 100, 5 cents. 1,000 times 1 over 100,000, 1 cent. 1 million times 1 over 10 million, 10 cents. So to do the expected value, what we do is after doing the value times the probability, we add all these together. So the -$1, the 20 cents, the 0.5, the 0.01, and the 0.10. And when we add up this column, it comes out to be -0.64. Thus, on average, over many tickets, we would expect to lose 64 cents for every lottery ticket purchased. So if you buy, say, 1,000 lottery tickets, you should expect to lose about 1,000 times 64 cents, or $640. Now, something else that goes along with probability is the gambler's fallacy. The gambler's fallacy is the mistaken belief that a streak of bad luck makes a person due for a streak of good luck, or a streak of good luck will continue. So here's a scenario where we have to be careful of the gambler's fallacy. It says you are playing the coin toss game in which you win $1 for heads and lose $1 for tails. After 100 tosses, you are $10 in the hole because you have 45 heads and 55 tails. You continue playing until you've tossed the coin 1,000 times, at which point there's been 480 heads and 520 tails. The first question is this consistent with what we would expect by the law of large numbers? And after playing by more tosses, has it actually helped gain back any of the initial losses, or just made things worse? Well, here's how it's going to work. First off, after 100 tosses, there were 45% heads that showed up, 45 out of 100. After 1,000 tosses, now there's 480 heads out of 1,000 tosses, which is 48% heads. So we can see how that's closer to a 50% here, which was what we would usually expect to see with the heads or tails, 50-50 chance of heads or tails. So it is consistent with the law of large numbers, with more tosses getting closer to the expected theoretical probability and proportion of 50%. However, the amount lost is going to be $40. because there would have been $520 lost due to the tails, only $480 earned for heads. It comes out to be a $40 loss, which is worse than it would have been after 100 tosses. So this is how the gambler's fallacy can cause losses to accumulate, because ultimately, by the law of large numbers, things should tend to even out toward their theoretical probability. And if there's already losses going on, it's going to be very unlikely for them to be overcome just due to the law of large numbers and the probabilities.